Learn like a pro.
All right, let's jump right in. Think about this. We're constantly being pushed on from every single direction by a force we can't even see. I'm talking about pressure. It's everywhere, shaping our entire world, but it's invisible. So how in the world do you measure something like that? Well, today we're going to build the architect's blueprint for it. We're going to learn how to visualize the invisible and understand the actual weight of the air all around us.
You know, it all kind of starts with this paradox. If you could shrink down to the microscopic level, what you'd see is just pure chaos. I mean, countless tiny air molecules zipping around, bouncing off of everything like a cosmic game of pinball. But here's the crazy part. When you zoom back out, all of that random, chaotic energy, it organizes itself. It becomes this single, steady, totally measurable force. And that's what atmospheric pressure is. It's just the grand total, the combined weight of all those tiny little collisions pushing down on us.
Okay, here's the best way to wrap your head around this. I want you to imagine that we're all living at the bottom of a giant, invisible ocean. But instead of water, it's an ocean of air. And just like a real ocean, all that air piled up above us has weight, a lot of weight. And it's pressing down on you, on me, on everything, from all sides every single second of the day.
So if we want to get a little more technical, what we're really talking about is the average force from all those tiny collisions spread out over a specific area. Now, at sea level, we've kind of standardized this pressure. We call it 1 atmosphere, or 1 ATM. And it turns out that amount of pressure has just enough oomph to hold up a column of mercury that is exactly 76 centimeters high. Now remember that number, 76 centimeters. It's going to be a really big deal.
Okay, so how do we actually measure the weight of this invisible ocean of air? I mean, you can't just put it on a scale, right? For that, we need our very first tool in our architect's toolkit. It's called the barometer. And honestly, it's a device of beautiful, elegant simplicity designed to do just one thing: weigh the air.
The way a barometer works is actually just a simple balancing act. Picture this. You've got this open pool of mercury. The atmosphere, our air ocean, is constantly pushing down on the surface of that pool. And that downward push is exactly strong enough to hold up that 76-centimeter column of mercury inside the glass tube. And here's the clever part. At the very top of that tube, there's a vacuum. No air, which means no pressure. So there's nothing pushing back down from inside the tube. It's a perfect, visible scale, with the air on one side and the mercury on the other.
Okay, now here's a super important detail, so listen up. What happens if you tilt the tube? The length of the mercury column might get longer, sure, but its vertical height, how tall it is from top to bottom, will stay at exactly 76 centimeters. This is absolutely crucial to understand. Pressure couldn't care less about the shape of the container or the angle you're holding it at. All that matters is the vertical depth of the liquid. That's it.
So this all leads to a pretty logical question, doesn't it? I mean, if this pressure is really just the weight of all the air piled up on top of us, does that weight ever change? Is it the same amount of pressure everywhere you go on the planet?
And the answer is a big, fat no. It's definitely not the same everywhere. Just take a look at what happens with altitude. Down at sea level, you've got that deep, heavy ocean of air pressing down, so the pressure is high. But what happens when you climb a mountain? Well, you've climbed through some of that air, right? So there's less of it above you. Less air means less weight pushing down, so the atmospheric pressure is lower. And sure enough, the mercury column in your barometer drops to reflect that.
All right, so the barometer is fantastic for measuring the big, wide open atmosphere. But what if you want to measure the pressure of a gas that's trapped in a container? Like in a chemistry lab or something. For that, we need a different kind of tool. We need something that creates a direct head-to-head showdown, a tug of war between our gas and the atmosphere.
And this is that tool. It's called a manometer. At its heart, it's just a simple U-shaped tube with some liquid in it. One end of the U is open to the air, to the atmosphere. The other end gets hooked up to your container of gas. And that liquid in the middle, that becomes the scoreboard in this pressure battle. It literally shows us who's winning the push of war, the gas on the inside or the atmosphere on the outside.
So in this little tug of war, there are really only 3 ways it can play out. Scenario 1, the liquid is perfectly level on both sides. That means it's a tie. The gas pressure is exactly the same as the atmospheric pressure. Scenario 2, the gas pushes the liquid down on its side. Well, that means the gas is pushing harder. It's winning. And scenario 3, the atmosphere pushes the liquid down on its side. Now the atmosphere is winning. And that little difference in height, what we call h, that's not just a random length. It's the key. It tells you exactly how much stronger one side is than the other. It's the margin of victory in our little pressure battle.
So, we've got the barometer, we've got the manometer. They seem like different tools with different setups and, maybe different math. But what if I told you there's a secret, a single, powerful, and almost ridiculously simple rule that unlocks all of these problems? A barometer, a manometer, even a super complicated one with 2 or 3 different liquids, they all bow to this one rule.
This is it. This is the architect's master key. It's the one thing you need to solve any of these problems. I like to call it the law of the line. And trust me, once you see it, everything is going to click into place.
So here it is, the big secret. The rule is simply this. If you have a single, continuous liquid, the pressure at any 2 points on the same horizontal level is always equal. That's it. Pressure on the left equals pressure on the right. That's the whole game. All you have to do is find the lowest point where the liquids meet, draw a horizontal line right through it, and then just balance everything that's pushing down on the left side of your line with everything that's pushing down on the right.
Okay, let's put this master key to the test. Let's say we have a U-tube with some water and some other unknown liquid, liquid X. We measure it, and the water column is 8 centimeters high, while the column of liquid X is 10 centimeters high. So, step 1, we draw our line at the interface, the lowest point where they meet. Step 2, balance the pressures. The pressure from that 8 centimeters of water on the left has to equal the pressure from the 10 centimeters of liquid X on the right. Now think about that for a second. It takes a taller column of liquid X to balance a shorter column of water. What does that tell you? It tells you liquid X must be less dense. And when you run the simple math, you find out its density is exactly 800 kilograms per cubic meter. See? Simple.
So there you have it. We've basically assembled a complete blueprint for understanding and measuring pressure. Let's just quickly lay out all the essential tools we've put into our Architect's Toolkit.
So your toolkit really just has 4 main parts. First, you've got the master equation, P equals H rho G. That just means pressure is a simple mix of vertical height, liquid density, and gravity. Second, the mercury advantage, the idea that using a really dense liquid like mercury lets you build smaller, more compact tools. Third, container irrelevance, the crucial reminder that it's only the vertical height that matters, not the shape of the glass. And finally, the big one, the golden rule, our law of the horizontal line. That's the key that unlocks every single one of these puzzles.
And really that's the whole point, isn't it? We started out with the pure chaos of invisible molecules bouncing around, and we ended up with a clean, elegant blueprint. It just goes to show you that with the simplest tools imaginable, literally just a ruler and knowing how dense a liquid is, we can map, measure, and actually understand the powerful, unseen forces that are shaping our world every single day. The simplest tools can truly build a blueprint of our world's invisible forces.